Okay, so before I get started, I would like to thank the organizer, Hoju Lee, for all his hard work in organizing this wonderful online seminar. And this provides me a good opportunity to learn how to make my own lecture videos. So uh, I'm going to talk about the constructions of Lagrangian translating solitons. So this talk is based on my preprint on the archive. So if you're interested in the details, then you can look up that paper. Okay. Okay. So let me start with some introduction about mean curvature flow. So mean curvature flow is basically a family of immersed submanifolds Ft moving in a speed equal to its mean curvature vector h of Ft. So by the first variation of volume, the mean curvature flow is actually a kind of negative gradient flow of the volume functional. That is, if we flow a compact manifold by mean curvature flow, then the volume will decrease in the fastest way. Okay, so in this sense, it is expected to be useful for studying the existence of volume minimizers. So the idea is that you start with some like any representative of a homology class, then you run the mean curvature flow, so that submanifolds start to shrink, and the volume is decreasing, and you will expect that at the end you will find some representative in that homology class with the least volume. So that's the idea. Okay. However, there are obstructions to this sort of nice picture. So the obstructions are the finite time singularities. So these are finite times Ts, such that when your time goes to Ts, the second fundamental form of the submanifold blows up. So indeed, actually, one can show that if the second fundamental form is bounded, then all the derivatives of the second fundamental form are also bounded, and therefore the submanifold converge to a smooth submanifold. So by short time existence, you can flow it, you can continue the flow beyond this time, and therefore the blow up of the second fundamental form actually provide a criterion of for the flow, such that you cannot continue the flow beyond this time. Okay. So here's a rough classification of finite time singularities. So we say a finite time singularity is type 1 if the second fundamental form blows up like 1 over square root of Ts minus T. So this kind of singular behavior is modeled on the homothetically shrinking solutions to mean curvature flow. For example, if we consider the standard sphere S2 and multiplied by a scale of square root of minus t, here t is negative, then it is not hard to show that this is a mean curvature flow. And as t goes to 0, the spheres shrink to a point, and the second fundamental form blows up like some constant c over square root of minus t. So this is the kind of type 1 behavior. So, so if it is not type 1, then it is called type 2. So this is a very rough classification. And therefore, the type 2 singularity does not have a specific rate of blow up. So it is harder to control. So, however, there's still some way to study the structure of a type 2 singularity. Okay, so so let's assume there's a type 2 singularity happened at time ts. So there's a rescaling procedure, usually called the type 2 blow up, or if you're familiar with Ricci flow, then it is the analog of the Hamilton's blow up. So using this rescaling procedure, one produces a sequence of mean curvature flows. So I denote it by FJS. And this family, this sequence of flows converge to a limiting flow called F infinity S. And so the type 2 condition will ensure that the limiting flow, the time parameter for the limiting flow, can be defined on the whole real line. And therefore, it is called an internal solution. Okay. So once you get a type 2 finite time singularity, you can use the Hamilton's blow up or type 2 blow up to produce a limiting flow, which is the eternal solution to the mean curvature flow. And that eternal solution basically tells you the infinitesimal structure of the near the singularity. So we will call this kind of eternal solution as type 2 singularity models. Okay, so an important class of eternal solutions to the mean curvature flow is the so-called translating solitons. So these are the solutions to mean curvature flow that translate in the Euclidean space in a fixed direction. Okay, so here's the idea about how we produce the type 2 blow up. So the initial data here is a kind of a figure 8 curve in the plane. So if you run the mean curvature flow, it will start to shrink, and at finite time, it will shrink to a point. And this is a type 2 singularity. Okay, so how do we study the type 2 singularity? Well, so we first mark each point of maximal curvature. So it is this red points here. So if we run the mean curvature flow, it will start to shrink. So this point will move, but we still trace this point. So, but since it at the end, the whole thing shrinks to a point, so we cannot see the structure in the ordinary scale. And therefore, we have to rescale the curve around this point of maximal curvature. Okay, so we rescaled it. such that the circle of curvature stays in the same size. So this is a rough idea. So no, this is not like this. So once it starts to shrink, we do a rescaling to fix the size of the radius to the circle of curvature. Okay, so the circle of curvature becomes smaller, but we rescale it such that it becomes the unit size. And at the end, the whole thing will converge to a non-compact curve. So although the original curve is closed, but after you do the rescaling and taking the limit, you will get a non-compact limiting curve. So this curve it looks like this, and it is called the Green Reaper, and it is a translating soliton, translate in this right-hand side direction. Okay. Okay, so let me give you the precise definition for the translating solitons. Okay, so the translating solitons is just submanifold satisfy this equation. So basically, the mean curvature vector is equal to a perpendicular part of some fixed vector in Euclidean space. Okay, so if I've got a translator, then we can produce an eternal solution by translate it in the minus t direction. So this ft will be an internal solution to the mean curvature flow. Okay, so I think the simplest non-trivial example of a translator is the so-called Green Reaper. So this is just what we have seen in the previous slide. So it is defined by this parameterization. So it is a graph. It is a graph over this y-axis. So the graph function is a minus log cosine. So this is a translator with translating direction to the right. Okay, so we will see this curve again later. Okay, so the translators have some nice variational property. So in fact, if we consider a function f defined by inner product of the position with the fixed vector t, then we can define a kind of weighted volume Vf. So the weighted volume is just you multiply the ordinary volume dVl by this exponential to the minus f over 2. Okay. So integrate this weighted volume form on the submanifold L, you get the weighted volume of L. So you can compute the first variation of this F volume in the direction of some normal vector field C. So this L here is often non-compact. So therefore, it is necessary to take C to be compactly supported. So if you compute the first variation, what you will get is that the gradient vector field of this F volume is exactly equal to the vector appeared in the translated in the definition of translators. And therefore, the translators are just critical points of this F volume. So if you're a fan of minimal submanifolds, then there's an alternative way to think of the variation property of translators. And in fact, they are just minimal submanifolds with respect to a metric G tilde, which is conformal to the original Euclidean metric. Okay. So you can also study translators using the minimal submanifold theory. Okay, so next I will talk about Lagrangian submanifolds, since I will study the Lagrangian translators. So Lagrangian submanifolds are submanifolds of some symplectic manifolds. So I will start with the introduction about the symplectic manifold. So let X2M be a smooth, even dimensional manifold, and together with a non-degenerate closed two form omega, then this pair X omega is called a symplectic manifold. So if your X is given a Riemannian metric G bar, then there's always a compatible almost complex structure J, such that if you plug in J into the first position of G bar, then you get the omega. So the typical example would be the even dimensional Euclidean space R2M with coordinates x, j, y, j. So the symplectic form omega naught is just the weight the dxj with dyj and sum them up. So so there's an almost complex structure compatible with the Euclidean metric. So this is just defined by a kind of rotation by the 90 degree. So it sends the ddxj to the ddyj, and it sends the ddyj to the minus of ddxj. So it's just a rotation by a 90 degree counterclockwise. Okay. So a half-dimensional submanifold L is called Lagrangian if you restrict the symplectic form omega onto L is equal to 0. That is, if you plug in two tangent vectors to L into omega, you get 0. Okay. So together with the Riemannian metric and the compatible almost complex structure, there's a more geometric description for the Lagrangian submanifold, saying that this compatible almost complex structure J actually induces an isomorphism between the tangent and normal bundle of L. So, so the Lagrangian submanifolds are in some sense generalization of plane curves, because normal vector of a curve is just the tangent vector of the curve rotate by a 90-degree. So this is like you apply the almost complex structure to the tangent bundle and you get normal bundle. Okay. So furthermore, J is not only just almost complex structure, but a complex structure. Then this triple xj omega is a Kähler manifold with Kähler metric G bar. So we call this Kähler metric G bar Kähler Einstein, or Ke, if its Ricci curvature is proportional to itself. Okay, so there's a nice thing about the Kähler Einstein manifolds. So if you have a Lagrangian submanifold in the Kähler Einstein manifold X, then the mean curvature vector actually defines a one form on L. So so basically you just interior product the mean curvature vector with the symplectic form, and you get a one form on the ambient space. Then you restrict on L, then you get the one form. So this this one form, I would denote it by omega tilde H. Okay. Okay. So actually, given any normal vector field, then you can always apply this this operation to obtain a one form. So because this vector mean curvature vector is special, so we will give this one form a name. So let's call it the mean curvature form. Okay. So if the ambient space is Kähler Einstein, then one can show that the mean curvature one form actually gives you a closed one form, and it represents a cohomology class. Okay, so what's special about having a closed one form? Well, once you compute the derivative of omega in the direction of the mean curvature vector, so by Cartan's homotopy formula, what you will get is the exterior derivative of this omega tilde H. So if the ambient is Kähler Einstein, this gives you 0. So therefore, the Lagrangian condition, so therefore, if omega is 0 on L, then it will not change infinitesimally in the mean curvature direction. Okay. So this result sort of give you an idea that whether the mean curvature flow will actually preserve the Lagrangian condition. Okay, so this is true. So Smolsik actually shows that the Lagrangian condition is preserved by the mean curvature flow if the ambient space is Kähler Einstein. And therefore, it is reasonable to talk about Lagrangian mean curvature flow. Not only in R2, just in any Kähler Einstein manifold, or Lagrangian translating solitons. So now this is in R2 2m. Okay. Okay, so assume that we have an additional structure, capital omega. So this capital omega is a parallel holomorphic M0 form on X. Then this quadruple will be called the Calabi-Yau structure. Then once you get the Calabi-Yau structure, the Caylor metric G bar will be Ricci flat. And therefore it is automatic Caylor-Einstein. So if we've got a Lagrangian submanifold in a Calabi-Yau manifold, then the Lagrangian condition will imply that if you pull back this Calabi-Yau structure, capital omega, to L, then what you get is an M form, and this M form will be the volume form times a unit complex number. So we can write it as exponential of some I theta L. So this is the phase function on L, and which is just a map from L to U1. And we can take sort of the logarithm of this phase function to get a multi-valued function theta L, and this will be called the Lagrangian angle of L. Okay, so the typical example, R2M or C to the M, we have the parallel holomorphic M0 form omega naught, just the dz1 which to dzm. So this gives you a Calabi-Yau structure on C to the M. So if there's a Lagrangian submanifold such that the Lagrangian angle is a constant, then actually one can show that if you pull back the real part of this rotation of Calabi-Yau structure, you get the volume form of L. Okay. So in this case, we said L is calibrated by this real part of e to the minus I theta bar omega. So this calibrated, this notion is invented by Harvey and Lawson. So they used this notion to actually define, to provide a tool to find the minimal submanifolds. Okay. So in our case, if the Lagrangian angle is constant, then this Lagrangian submanifold will be called the special Lagrangian submanifold with phase theta bar. And what is good about a calibrated submanifold is that they are actually volume minimizers in the homology class. And therefore, special Lagrangian submanifolds are volume minimizers.